Hello everyone, welcome back to my YouTube channel. Today's topic is classification of electrical networks. Classification of electrical networks. Electrical networks are the fundamental aspects of electrical engineering. Understanding their classification is essential for analyzing and designing circuits. Passive and active networks. Passive networks contain only passive components like resistor, capacitor, and inductors, while active networks include active devices such as transistor or a operational amplifier. Passive networks. These networks do not generate power but rather dissipate or store it. They are primarily composed of a resistor, capacitor, and an inductor. Active networks. These networks have the ability to amplify or generate power. They typically contain active devices such as transistor, operational amplifier, or a voltage sources. Linear and non-linear networks. Linear networks exhibit a linear relationship between inputs and output signal, while nonlinear networks do not. Linear networks. These networks follow the principle of superposition, meaning that the response to multiple inputs is the sum of the response to each individual input. Linear networks are characterized by their consistent response to change in input, making them predictable and easier to analyze. Nonlinear networks. The output of these networks is not directly proportional uh, to the input, making their behavior more complex and difficult to predict. Nonlinear networks are often used in applications where nonlinear behavior is desirable, such as signal processing and power electrons. Time invariant and time variant networks. Time invariant networks have parameters that remain constant over time, while time variant networks have parameters that change with time. Time invariant. The behavior of this network is consistent regardless of when the input signal is applied. This makes them similar to analyze and model. Time variant. The parameter of these networks can change due to factors such as temperature, variations, aging of components, or external control signals. Examples include circuit with switches, variables, resistors, or components that exhibit a temperature-dependent behavior. Lumped and distributed networks. Lumped networks are characterized by components that are small compared to the wavelength of signal, while distributed networks have components that are comparable in size to the signal's wavelength. Lump networks. The size of the components is small enough to the signals travel. Time through the network is negligible. Distributed networks. In these networks, the sign travels through the network with a finite speed, and its properties can change as it travels. Example, transmission lines and antennas are example of distributed network. Resistive, capacitive, and inductive. Networks can be classified based on the dominant type of component they contain, resistive, capacitive, or inductive. Resistive networks. These networks primarily consist of resistor, which opposes the flow of current. Capacitive networks. These networks are characterized by capacitor, which store electrical energy in an electric field. Inductive networks. These networks are dominated by inductors, which stores electrical energy in a magnetic field. Series and parallel. Series and parallel connections are two fundamental ways to connect components within electrical networks. A series network. Components are connected in a single path, so the same current flows through each component. The total resistance in a series network is the sum of the individual resistance. Parallel networks. Components are connected in multiple paths, so the voltage across each component is the same. The reciprocal of the total resistance in a parallel network is the sum of reciprocals of the individual resistance. Symmetric and asymmetric networks. Networks can be classified as symmetric or asymmetric based on their structure and component arrangement. Symmetric networks. These networks have identical components and symmetrical arrangement, resulting in balanced behavior. Asymmetric networks have different components or an asymmetrical arrangement, resulting in unbalanced behavior. Balanced and unbalanced networks. Balanced networks have equal current flowing through each phase or a branch, while unbalanced networks have unequal currents. Balanced networks. These networks are designed to operate with equal current distribution in each phase, leading to efficient power delivery. Unbalanced networks have unequal current distribution, which can lead to inefficiency and potential problems with the power delivery. The examples are three-phase power system are commonly used in industries and are typically designed to be balanced. Planar and non-planar networks. Planar networks can be drawn on a plane without any wires crossing, while non-planar networks cannot. Planar networks, these networks can be drawn on a flat surface without any wires overlapping. This simplifies analysis and design. Non-planar networks, these networks have components arranged in a way that requires wire to cross, making it impossible to draw them on a plane without overlapping. The example, many practical circuits, especially those involving complex interconnections, are non-planar.